Good afternoon. Am I audible? Hello? Am I audible? Are you able to hear my voice? Okay. Okay. So we start our class. Now, before going to start today's class, first we discuss about what we have done in the last class. Yesterday, after completion of mean value theorem problems, we have started the Taylor and Maclaurin series. After that, we have stopped the class on. Now, continuation of the topics. Next topic will be partial derivatives and total derivatives. That is partial and total derivatives only. According to GATE syllabus, the first topic is mean value theorem, second one is Taylor and Maclaurin series, third one is partial and total derivatives. So today we start the partial and total derivatives topic only. Right? Now, let us write the first name of the subtopic. Partial and total derivatives. In this subtopic, partial and total derivatives, first we read the Euler's theorem for homogeneous functions. Euler's theorem for homogeneous functions. After that, we'll discuss about the method of finding the derivatives of explicit, implicit, composite functions only. In that, we write the total derivative, total differential, chain rule for partial differentiation like this, all these. And then we write the Jacobian of transformation on. So we'll discuss about all these in this subtopic partial and total derivatives. So let us start with the Euler's theorem for homogeneous functions. In the differential equation topic, already we have written the definition of homogeneous function. Definition of homogeneous function. In the functions, you may have the transcendental functions, non-transcendental functions. Non-transcendental functions are algebraic functions only. So algebraic functions, transcendental function. In the differential equation topic, already we have discussed about the homogeneous function and how to find the degree of the homogeneous function. Once again, we read the method of writing the degree of the algebraic function, transcendental function, and then write the Euler's theorem for homogeneous functions. So first we start with the homogeneous function. Again, I am not writing the definition of homogeneous function because already we have written the definition of homogeneous function in the differential equation topic. But here we discuss about the method of writing the degree of the algebraic function when it is homogeneous, a method of writing the degree of the transcendental functions, in which the first bit algebraic function. If f of x comma y equal to p of x comma y divided by q of x comma y, comma, where p of x comma y and q of x comma y are homogeneous functions with degree small a and small b respectively. respectively. Then f of x comma y is a homogeneous function with degree n equal to a minus b. That is numerator function degree minus denominator function degree only. Is a homogeneous function with the degree n equal to a minus b in x and y, because it is a function in terms of x and y. So if any function is given like this, some function of x and y by some function of x and y, then we check like this, homogeneous or not. If it is homogeneous, we write the degree directly only. Numerator function is p, denominator function is q. When p and q are homogeneous functions with the degree a and b, that is a is the degree of the numerator function p, b is the degree of the denominator function q only. When p and q are homogeneous functions with some degree, then the whole function p by q whole function will be homogeneous function with the degree a minus b only. That is numerator degree minus denominator degree only. In general, the function is like this. Suppose x square plus xy minus 4y square only. It is a function in terms of two variables. It is some function in terms of two variables. X square plus xy minus y square. Function in terms of two variables only. In the first term, the power of x is 2. In the second term, the sum of the powers of the variables, sum of the powers of the product of the variables. In the first term, single variable is present. In the second term, product of two variables is present. Last term, single variable is present only. When you have a product of two variables like this, then we observe the sum of their powers only. 1 plus 1, 2 only. In the last term also, the power of the variable is 2 only. In every term, the powers of the variables is same. Therefore, it is a homogeneous function in general like this. In each and every term, the powers of the variables is same, then homogeneous function. But in this function, in every term, power is 2 only. Therefore, it is a homogeneous function with the degree 2 only. But always you may not have like this x square plus 4xy minus y square like this, just a numerator function. Always you may not have function like this. Sometimes you may have this something by something also. If we have a something by something like this, then we follow this method only, this algebraic method. This is for only algebraic functions only. So let us write the example. Example number 1. F of x comma y equal to x cube plus y cube divided by x power 3 by 2 plus y power 3 by 2 only. This is some function of two variables. It is some function of two variables x and y only. And this is free from, this total function is free from all the transcendental functions. It is free from all the transcendental functions only. Transcendental function means exponential, logarithmic, next trigonometric, inverse trigonometric, hyperbolic, inverse hyperbolic. Logarithmic, exponential, trigonometric, hyperbolic. These are called transcendental functions. So this function is free from all these transcendental functions. So it is purely algebraic function. That is something by something form. That is numerator by denominator form. Since it is in the form of f of x comma y equal to p of x comma y by q of x comma y like this. The function is in the form of like this. So whenever function is like this, like above, we check the homogeneous or not. Here, numerator function is homogeneous function with the degree 3, because in the numerator, for every term, the power of the variable is same only. So numerator is a homogeneous function with the degree 3. Next, denominator. In the denominator also, for every term, the power is same. Denominator function is a homogeneous function with the degree 3 by 2 only. When numerator and denominators are homogeneous function with some degree, then the whole function will be homogeneous function with the degree a minus b only. That is numerator degree minus denominator degree only. Here, f of x comma y is a homogeneous function with degree n equal to numerator degree minus denominator degree. Numerator degree is 3, denominator degree is 3 by 2 equal to 3 by 2, right? So this degree may be any number. That may be positive fraction, negative fraction, or negative number, or 0 or positive number, any number. This may be any some number only. So finally, this function is a homogeneous function with a degree 3 by 2 only. Right? Like this, we can check the function is homogeneous or not. But is homogeneous, we can add the degree of the homogeneous function. This is for algebraic functions. Next, we'll discuss about transcendental functions only. Second bit. Transcendental function. Transcendental function means logarithmic, exponential, trigonometric, hyperbolic, inverse trigonometric, inverse hyperbolic. If f of x comma y equal to transcendental function. Transcendental function is a function of transcendental function is a function of g of x comma y, comma, where g of x comma y is a homogeneous function with degree 0, then f of x comma y is a homogeneous function with degree 0. When f of x comma y is equal to transcendental function of g of x y. Here transcendental means that may be exponential, logarithmic, trigonometric, inverse trigonometric, hyperbolic, inverse hyperbolic, anyway. So transcendental function of g of x comma y means like this. Let us take this sine. Sine is a function of some variable. So sine is a function of x. So sine is a function of variable x only. Next here, sine is a function of y like this. Sine is a function of x square plus y like this. So this is the g of x comma y only. Sine is a function of single variable. Sine is a function of single variable. Here sine is a function of two variables. So we are taking inner function as g of x comma y only. When this g of x comma y is, that is inner function g of x comma y is homogeneous function with the degree 0, then only this sine function will be homogeneous function with the degree 0. Otherwise, not a homogeneous function. For any transcendental function, the same thing always. Example. Example number 1. F of x comma y equal to sine inverse of x square plus xy divided by y square minus 2xy. Sine inverse. First of all, sine inverse is the inverse trigonometric function. It is a transcendental function. And this transcendental function is in the form of like this. F of x comma y equal to sine inverse of g of x comma y only. Sine inverse of g of x comma y, like this. If we compare this function with this, in place of g of x comma y, we have x square plus xy divided by y square minus 2xy only. So for this, whenever g of x is homogeneous function with the degree 0, then the sine inverse function will be homogeneous function with the degree 0 only. Only g of x comma y is algebraic function. So this inner function is algebraic function. For this algebraic function, we can use the previous one only, because numerator by denominator only. The numerator is homogeneous function with the degree 2. Denominator is also homogeneous function with the degree 2. Therefore, this g of x comma y inner function is a homogeneous function with the degree 0 only, because 2 minus 2, 0. So inner function is homogeneous function with the degree 0. Therefore, sine inverse is a homogeneous function with the degree 0. Here, f of x comma y is a homogeneous function with degree 0. That's it. Like this we can check. One more example. Example number 2. F of x comma y equal to e power x plus y divided by x. Since it is in the form of f of x comma y equal to e power g of x comma y. For this exponential inner function g of x comma y equal to x plus y by x only. Again, this g of x comma y is algebraic function. So check the algebraic function is homogeneous or not. X power is 1, y power is 1, here x power is 1. Numerator is a homogeneous function with the degree 1. Denominator is a homogeneous function with the degree 1. So 1 minus 1, 0. This inner function g of x comma y is homogeneous function with the degree 0. Therefore, exponential function is a homogeneous function with the degree 0. Here f of x comma y is a homogeneous function with degree 0. Example number 3. Example number 3. F of x comma y equal to log of 4x cube plus x square y divided by y cube plus x y square. Log is a transcendental function. Since this function is in the form of like this, f of x comma y equal to log of g of x comma y only. In place of g of x comma y, we have this function. Power 3, 2 plus 1, 3. Numerator is homogeneous function with the degree 3. Denominator is also homogeneous function with the degree 3. Therefore, inner function is homogeneous function with the degree 0. That is why log function is homogeneous function. Here, f of x comma y is a homogeneous function with degree 0. Next, example number 4. F of x comma y equal to tan of x plus y divided by, or x square plus y square divided by x plus y. since it is in the form of f of x comma y equal to tan of g of x comma y. Now for this transcendental function, inner function is x square plus y square by x plus y. This inner function is a homogeneous function, but with the degree 1, not degree 0. That is why tan function is not a homogeneous function only. Here f of x comma y is not a homogeneous function. Not a homogeneous function, because inner function is not a homogeneous function with a degree 0. Inner function is homogeneous function, but not degree 0. It is degree 1. For any transcendental function, inner is degree 0, then only this will be homogeneous with the degree 0. Otherwise, not a homogeneous function. One more example. Example number 5. F of x comma y equal to cos of x square plus y divided by x cube plus y cube. Since it is in the form of f of x comma y equal to cos of some function g of x comma y. Now g of x comma y is algebraic function x square plus y by x cube plus y cube. This g of x comma y is not a homogeneous function because the numerator function is not homogeneous function. Denominator is homogeneous function, but numerator is not a homogeneous function. First of all, inner function is not a homogeneous function, so main function is not homogeneous function. In the above, inner function is homogeneous, but main function is not homogeneous. Like this, we can check the homogeneous or not for transcendental functions and also algebraic functions. Next, note point number 1. If f of x comma y is a homogeneous function with degree n in x and y, then f of x comma y equal to x power n into some function of y by x, y power n into function of x by y. Already we have written this as a note point in the differential equation topic only, this note point. Right? If any function is homogeneous function with some degree n, then that function will be written as function of y by x into x power degree, function of x by y into y power degree. Like this we can write. Or if any function is given in the form of like this also, directly that is a homogeneous function. For example, the function is given like this, f equal to x power minus 2 into tan of y by x. It is a function of y by x. This is in the form of x power into function of y by x. So this is this function, this is like this only. So directly it is a homogeneous function with the degree minus 2 only. Suppose if f equal to like this, y power 4 into cos of x by y, or cos of x square by y square, like this only. Again, this is in the form of y power n into function of x by y only. So if any function is given like this, directly we can set homogeneous function or not. This is a homogeneous function with a degree like this, n equal to 4. So in this way also we can set homogeneous function. So in the homogeneous function, we have seen how to check the function is homogeneous or not. If it is homogeneous, how to write the degree like this one for both algebraic and transcendental functions. Next, we have the Euler's theorem. Theorem number 1. Name of the theorem is Euler's theorem for homogeneous functions. Statement of this. If u equal to f of x comma y is a homogeneous function with degree n in x and y, then the first result is x into dou u by dou x plus y into dou u by dou y equal to degree n into u or degree n into f. When function is a function of two independent variables and also it is homogeneous function with some degree, then directly we can add the result of this x into ux plus u into y, x into ux plus y into uy. This result is directly degree into the same function u only. Second result, x square into dou square u by dou x square plus 2xy into dou square u by dou x dou y plus y square into dou square u by dou y square equal to degree n into degree minus 1 into u or degree into degree minus 1 into f. Out of these two results, the first result is a previous gate question. Directly, this first result is a previous gate question. And in this theorem, we have written these two results only for single function, u equal to just function of x and y. But always u may not be single function. Sometimes u may be sum of many functions also. U equal to f plus h plus g plus like this also. Now we are at the same two results for sum of two functions. The same thing for any number of functions. We write that as a note point. Note point number 1. If u equal to h of x comma y plus g of x comma y, where h of x comma y and g of x comma y are homogeneous functions with the degree m and n respectively, then the first result is x into dou u by dou x plus y into dou u by dou y equal to. Already we know the result of this for single function, but here we require the same result for sum of the two functions. U may be sum of two functions, three functions, more than three also like this only. In the sum of many functions, all functions are homogeneous with some degree, then only we can write the result only. Out of these two, any one is not homogeneous, we cannot write the result directly only. In such case, we have to find the derivatives only. So here h and g are homogeneous. That is why without finding the derivatives, directly we can add the x ux plus y uy value on. Now first we write the correspond to h function, write the same result. Next correspond to g, we write the same result, and then we add both only. Correspond to h function, m into h. Next correspond to g, n into g only. The second result, x square into dou square u by dou x square plus 2xy into dou square u by dou x dou y plus y square into dou square u by dou y square equal to. Like above result, we are this result for sum of two functions only. Correspond to h function, result is m into m minus 1 into h plus correspond to g, n into n minus 1 into g only. Like this we can add the result on. This is for sum of the two functions. Same thing for sum of 3, 4, like this also. But the condition is in the sum of many functions, all functions should be homogeneous only. Otherwise, we cannot find. Next, we have the another note point. Note point number 2. If u of x comma y is not a homogeneous function, but f of u is a homogeneous function with degree n in x and y, then the first result is x into dou u by dou x plus y into dou u by dou y equal to n into f of u by f dash of u. Function of u by function of u. Let us suppose this is some function of u. Using this, we get the second derivative result. Second bit, x square into dou square u by dou x square plus 2xy into dou square u by dou square u by dou x dou y plus y square into dou square u by dou y square equal to phi of u into phi dash of u minus 1. Directly, the given function u is not a homogeneous function, but function of u. If you add the u as a variable in the function, then such a function is homogeneous function. Then we can add the two results like this only. Example like this. Sine of x square plus y square plus the denominator x plus y. Now let us suppose this is u. First of all, it is a sine trigonometric function and it is a function of two variables. U is not a homogeneous function only because for this trigonometric function, inner function is not a homogeneous function with the degree 0. So directly u is not a homogeneous function. Suppose if I write some function of this u variable, if I write some function of this variable, then that function may be homogeneous function. Now I am bringing the sign this side. That becomes sine inverse of u equal to x square plus y square divided by x plus y. Sin inverse of u. That is some function of u. Let us suppose this is some function of variable u like this one. Directly, u is not a homogeneous function, but f of u is a homogeneous function with a degree 2 minus 1, 1. F of u, sin inverse of u is a homogeneous function with a degree 1. It is not a homogeneous function. So for this type of function, we use these two results. Let us do the problems on this. Problem number 1. If, or we write the problems in the next page. Problem number 1. If u equal to log of x power 4 plus y power 4 divided by x plus y, then the value of x into dou u by dou x plus y into dou u by dou y is option A 6, option B 5, option C 4, option D 3. It is a 2020 IES question, 2 marks problem, because all IES questions are 2 marks problems only. It is a recent exam, IES examination question. We are given some function of 2 variables. We are given some function of 2 variables. That way it is a transcendental function because log is a transcendental function. And we are asked to find the value of this. We are asked to find the value of this one. It is just like x into dou u by dou x plus y into dou u by dou y. One method is, for the given function u, we have to find the dou u by dou x, next dou u by dou y. After that, we multiply x into dou u by dou x and y into dou u by dou y. Then we add, so that we get the sum of these two only. It is an actual method. But before finding the derivatives, first we observe this only. The given function is homogeneous function. Directly we can add this result by using Euler's theorem only. If it is not homogeneous function, at least inner function is homogeneous function or not, we check it online. Now first check the log function is homogeneous or not. For transcendental function, inner function is homogeneous function with the degree 0, then only the main function log will be homogeneous function with the degree 0. Otherwise, not a homogeneous function. But the inner function is algebraic function. This algebraic function is homogeneous function with the degree 4 minus 1, that is 3 only. So inner function is homogeneous function with the degree 3, not degree 0. That is why log is not a homogeneous function. Whenever log is not homogeneous function, we write this log as function of u only. We write the u as a variable in some function only. And we check that function is a homogeneous function or not. When you bring the log this side, that becomes e power u only. E power u equal to x power 4 plus y power 4 divided by x plus y. This is a function of u. Directly u is not a homogeneous function. Directly u is not a homogeneous function, but function of u is a homogeneous function through this relation. Degree is 4 minus 1, that is 3 on. So for this function, we can add the result directly on without finding the derivatives. That is according to note point number 2. That is like this. According to this result. It is a 2020 IES question, 2 marks problem only. As well, all IES questions are 2 marks problems only. Okay, let us do this problem. The given function u of x comma y is not a homogeneous function. not a homogeneous function. But f of u equal to e power u equal to x power 4 plus y power 4 divided by x plus y is a homogeneous function with degree n equal to 4 minus 1 equal to 3. Now x into u suffix x, that is u suffix x is partial derivative of u with respect to x, that is dou u by dou x, plus y into u y equal to n into f of u by f dash of u1 equal to n is 3, f of u is e power u, its derivative is also same, equal to 3. That's all. It is the result. Now we write next step. Therefore, x into ux plus y into uy equal to 3. This is the result. So correct answer is 3. That is option D. It is a 2020 IS question. Next, problem number 2. If u equal to log of x square plus y square divided by x plus y, then what is the value of x into dou u by dou x plus y into dou u by dou y? Question mark. Option A 0, option B 1, option C u, option D e power u. Now we can tell the answer for this. It is also IS question, 2018 IS question. But both are similar problems only. And that too, both are transcendental functions, both are log functions, and we are asked to find the same result x ux plus y uy only. Now we can tell the answer for this directly on. Right. Most of them are saying that 1, right? What means that is option B. Correct. It is a correct answer. Like this, we will get simple question. Okay, let us do the next problem, problem number 3. And these two are IS question. One is 2020 and one is 2018. So 2018, 2020 are similar model questions only. Right. Next problem number 3. If u equal to x power minus 2 into tan of y by x plus 3 into y square into sine inverse of x by y, comma x greater than 0 and y greater than 0, then x square into uxx plus 2xy into uxy plus y square into uyy equal to option A 6u, option B minus 6u, option C u, option D 2u. Now tell me the answer for this. Like previous two problems here, u is a transcendental function because on right hand side we have the trigonometric function tan inverse, trigonometric function sine inverse. So u is a transcendental function. Then check whether it is a whether the function u is a homogeneous function or not. But in every option something is given, definitely it should be homogeneous function. May not be homogeneous function also. If it is not homogeneous function, then you have to find all the derivatives uxx, uxy, uyy on. If it is homogeneous function without finding the derivatives, we can add the result of this. That is the advantage. Okay. Now we'll check it. First of all, on the right hand side we have a sum of two functions only. We have a sum of two functions. This is one function. This is one function. Whenever it is sum of many function, check every function is a homogeneous function or not. Is it a homogeneous or not? Is it a homogeneous or not? Right, 6u is correct. If each function is a homogeneous function with the same degree, then only u will be homogeneous function. Otherwise, not a homogeneous function. But here, directly we can set homogeneous or not only, because this function is in the form of like this. Very first one is in the form of x power n into some function of y by x. And the second one is function of x by y into y power n. Both are in the form of like this. Therefore, first one is a homogeneous function with the degree -2. Second one is a homogeneous function with the degree 2 only. Both are homogeneous functions with a different degree. That is why u is not a homogeneous function. U is not a homogeneous function. So in this case, right hand side both are homogeneous functions with this different degrees. So we use the sum of two homogeneous functions result only. That is this. After Euler's theorem, we have written the first note point. When u equal to h plus g, h plus g, h and g are homogeneous functions, then we can write the result like this, using this result only. Let u equal to h of x comma y plus g of x comma y, comma, where h of x comma y equal to x power -2 into tan of y by x and g of x comma y equal to 3y square sine inverse of x by y or homogeneous functions with the degree m equal to -2 and n equal to 2 respectively. Then x square into uxx plus y, that is 2xy into uxy plus y square into uyy equal to corresponding to m, corresponding to this h function, m into m minus 1 into h, correspond to next function g, n into n minus 1 into g only, which implies x square into uxx plus 2xy into uxy plus y square into uyy equal to in place of m, write the minus 2. Minus 2 into minus 2 minus 1 into h plus 2 into 2 minus 1 into g only. Oh. Actually here for g function degree is 3. Only for degree 3 here option is there. So let us write the none option here. None of these. So these options were given only for in place of n 3 only. But in place of n, here we took the 2 only. So some other option. Right. Which implies x square into u xx plus 2xy u xy plus y square into u yy equal to minus 3 into minus 2 minus 6 minus into minus plus 6 6h plus 2g. Suppose here if it is 2, then 2 into h plus g. In that case, 2u only. Right? Suppose in place of 2, if we have 6, then this will be 6 into u only. So it is the answer. Therefore, answer is 6h plus 2g only. None of these. Or we can simplify this also. We can separate the here 6h. We can add this 6h as 4h plus 2h plus 2g. 2 into h plus g on. This is equal to 4h plus 2u also we can write down. Anyhow, this is none option. So none is the correct answer. Suppose in place of n, if you take 3, in place of n, if you take 3, then this will be 3 into 3 minus 1. 3 minus 1 is 2. 3 into 2, 6. From this, we are getting 6h. From this, we are getting 6g. So 6 into h plus g. So in that case, 6u is the correct answer. But here, in place of n, we took the 2 one. That is why this is the answer. That is none of this is correct. For n equal to 3, for the same function, a is the correct answer, 6u is. But for n equal to, it is the answer, 4h plus 2u or 6h plus 2g. This is for Euler's theorem. So on Euler's theorem, we have done 3 problems. Then we go to next page. In the next page, we start the total derivative. Total derivative. In the very first class of calculus, already we have discussed about the different forms of functions. Function is some relation in terms of variables. The relation may contain 2 variables or 3 variables or 4 variables like this only. But the function may be given in the form of explicit, implicit, composite. For these functions, we discuss about the methods of finding the derivatives on them. Explicit means like, once again I revise, x square minus x y plus 4 equal to 0 only. From this, we can write the y variable in terms of all other variables only. X square plus 4 divided by x only. If you are able to write the one variable in terms of other variable, that is general form like this, y equal to f of x or x equal to f of y also. If you are able to write the one variable in terms of other variables, then this type of relation or function is called explicit function. If you are able to express explicit function, one variable in terms of all other, then explicit function. For example, the relation is like this: x square minus xy plus y cube minus 4 equal to 0 only. From this relation, we cannot write x in terms of y, and also we cannot write y in terms of x. This is not possible. This is not possible for this. That is why this type of relation is called implicit relation, implicit function. This is explicit function. This is implicit function only. If you are able to express explicit, unable to express, that is internally connected by some relation, then this is implicit. If you are able to express, then explicit. Next, other form is composite function or function of function. Suppose u equal to f of x comma y. Again, x is some function of t, y is some function of t, like this. This type of relation is the composite function or function of function only. For these functions, we write the methods of writing the derivatives only. In which first one, total derivative. If u equal to f of x comma y comma where x equal to phi of t and y equal to psi of t, then the derivative of u with respect to t the derivative of u with respect to t is called the total derivative of u with respect to t, and it is denoted by du by dt. Therefore, du by dt equal to dou u by dou x into dx by dt plus dou u by dou y into dy by dt. This is about total derivative. The derivative of u with respect to t is called total derivative for this relation. What is the name of the relation? Composite relation or composite function. First of all, it is a composite function of one variable. Always the composite function may not be a function of one variable. That may be a function of more than one variable also, 2, 3, 4, like this also. Whenever the composite function is a function of one independent variable, its derivative is ordinary derivative, and this ordinary derivative is called total derivative. Right? And don't remember this formula, because always the function may not be given like this. The function may be function of more than one variable, and x and y may be function of more than one variable also. So don't remember this formula. Here I will show you how to write this formula directly from the given relation. Directly from given relation of any number of variables, composite function. Okay, and remember this. In this we have both partial and ordinary derivatives. This is ordinary. D means ordinary. Do means partial. D. Do. Do is for partial. D is for ordinary. Okay, I will show you how to write this. Now, from the given relation, first we draw the diagram. U is given in terms of two variables, x, y. Again, x and y are given in terms of some other variable. X is given in terms of t, y is given in terms of t only. Next, you can check it, t is given in terms of any other variable or not. After this, t is not given that in terms of any other variable. So we stop here. U is in terms of x and y in terms of t only. That's all. We stop here. And we have the starting variable as a function of last variable. Starting variable is u, last variables are same, that is only t. Starting variable is u, last variable is t only. So we write the starting variable as a function of last variable, that is u of t. Because of only one variable here, u is a function of one variable. Because of one variable function or function of one independent variable, its derivative is ordinary derivative. This ordinary derivative is called total derivative only. Now, here I will show you how to write this only. Just look at this. Starting variable is u, last variable is t. We start at u, we can go to t. We start at u, we can go to t. To reach t, we started u, we can go to t. To reach t, there are two ways. Through x we can reach, through y we can reach only. There are two ways to reach t only. The number of ways of reaching t, the number of ways of reaching t is same as number of terms in the derivative formula. How many terms here? This is one term, this is one term, sum of the two terms only. The number of ways of reaching the variable t from u is the number of terms in the derivative formula. That's all. Suppose if we have one more way like this, through z, if we can reach t, then you will have here one more term only. Dou u by dou z, dz by dt, like this only. But this is not there, so this is not there. That's all. This is a function. So we can start at u, we can go to t. To reach t, there are two ways. Through x we can reach, through y reach. Like that here, we can find the derivative also like that only. First, we started u. We started u. We go to x. Again, x to t. U to t through x only. Again, after reaching t, through y, if you want to go to t, then we started u. We go to y, and then y to t, like this only. In two ways we can reach only. In the same way, we write the derivatives only. U to x, one derivative, x to t, one derivative. Right? Now, first u to x. And remember one thing. In the differential equation topic, very first class of differential equation topic, already I told you that there are two types of derivatives. One is ordinary derivative, other one is ordinary derivative, other one is partial derivative. The ordinary or partial depends on the function of independent variables only. Whenever function is a function of one independent variable, derivatives are ordinary derivatives. Whenever function is a function of more than one variable, 2, 3, 4, like this, the derivatives are partial derivatives only. So depending on number of independent variables in the relation, we have the two different types of derivatives, ordinary, partial. That's all. Now look at here. U is a function of two variables x and y. That is why u to x derivative will be partial. Again, x to t. X is a function of single variable. So x to t means ordinary derivative. That's all. In this way, we can write the derivative. Now see this. Dou u by dou t equal to, in the first term, through x. U to x derivative is partial dou u by dou x. Next, x to t, dx by dt. This is one way. Through y, u to y is partial, that is dou u by dou y, and y to t is ordinary, dy by dt. That is why don't remember this as a formula. Like this, any composite function is given in terms of one variable or more than one variable. Just draw the diagram, and from the diagram write the formula directly on this. But remember that where it is more than one variable function or one independent variable function, check it on. Where it is one variable function or more than one variable. If it is one variable, ordinary derivative like this. If it is more than one variable, then partial derivative. Remember that. That's all. It is about total derivative. Next, total differential. Total differential. Previous one is total derivative only. It is total differential. If u equal to f of x comma y is a function of two independent variables x and y, then the total differential of u is given by is denoted by du. And it is given by du equal to dou u by dou x into dx plus dou u by dou y into dy. It is a total differential. It is similar to total derivative. The total derivative is like this: du by dt equal to dou u by dou t into dou u by dou x into dx by dt plus dou u by dou y into dy by dt. This is a total derivative. It is a total differential. Then what is the difference between these two? One is total derivative, other one is total differential. That is derivative, differential. It is only difference. Derivative means change in one quantity corresponding to change in other quantity only. That is change in u correspond to change in t only. Here, change in only one variable u only. Here, change in one variable corresponding to change in one variable. That is a derivative, differential coefficient. Here, change in only one quantity, not correspond to any other change only. Just change in u only. Here, change in u correspond to change in t only. That's it. Here, it is a differential coefficient or derivative. This is only differential only. It is also similar to previous only. Suppose this is not there. This is not there, not there, not there. Then same. Now, first we'll draw the diagram for this relation. The given relation is like this. U is in terms of x and y. That's all. And for this total derivative, the relation diagram is like this. U2 xy, again x2 t, y to t. That's all. It is the relation. U is in terms x and y are in terms of TR. But here U is in terms of only x and y. That is why we start at U, we go to x, we stop. We start at U, we go to y, we stop. That's all. U is a function of more than one variable. That is why U to x derivative is partial derivative dou U by dou x only. U to y derivative is partial derivative only. Here we start at U, we go to x. Next, after x, we go to t only. But here, after reaching x, we stop at x only. And then we write the change in x, because x is not depending on any other variable. Here, x is depending on other variable. That is why dx by dt. So u is depending on x, and x is not depending on any other variable. We start at u, we go to x, we stop there, and we write the change in x. That is dx only. We start at u, we come to y, and after reaching y, we write the change in y, like this. That's all. Just like the remember this one. If no t, then no dt. In that case, again, differential only same, right? This is about total differential. Next, third one. Chain rule for partial differentiation. Chain rule for partial differentiation. If u equal to f of x comma y, comma, where x equal to phi of r comma t and y equal to psi of r comma t, then the first result is dou u by dou r equal to, and the second result is dou u by dou t equal to. Now dou u by dou r equal to. Just look at this only. Compare this function with this function. The total derivative, we have taken this composite function. Now in this also we are taking the composite function. What is the difference between this and that composite function? Page number 10, F and 8F. The only difference is composite function of one variable in 8F only. In page number 10F, it is a composite function of more than one variable. It is the only difference. Otherwise, both are same one. Already I have shown you how to write the derivatives for a function of like this. Any number of variables, doesn't matter. Just draw the diagram, and from the diagram, try to write the formula. That's all. So let us draw the first diagram for the given relation, and then we write the formula. U is given in terms of two variables, x, y. Again, x and y are given in terms of two more variables, r, t. Here also, y is a function of r and t. After this, r and t are not given in terms of any other variable. Suppose r and t are given in terms of any other variable, then we extend like this only, but no other extension. So we stop here. Starting variable is u, and last variables are two different variables, not same variables, two different variables, r and t only. So we write the starting variable u as a function of last two variables, u of r comma t. So here u is not a function of one variable, u is a function of more than one variable. That is why its derivatives are partial only. U with respect to r is dou u by dou r, and u with respect to t is dou u by dou t only. Like this. So just like page number 8F, like this diagram, and from the diagram already you know the method of writing the derivative formula. The same way here we write, but the only thing is have to To write the derivative, we check whether the function is a function of one variable or more than one variable. One variable, ordinary. More than one variable, partial. That's all. It is the only difference. So we started u, we go to x. We started u, we go to x. And x to r. Similarly, u to y, y to, yes, we started u, we go to x, x to r. In the same way, to reach r through y also we can reach u to y, y to r only. But u to x is partial, x to r is also partial because x is function of more than one variable. So all derivatives are partial derivatives here. First, u to r. U to r. That is partial derivative dou u by dou r. We can start at u, we can reach r through x through y like this. So first u to x, that is partial derivative dou u by dou x, again x to r, dou x by dou r, plus dou u by dou y by dou r. Similarly, you can write the next one also. Instead of u to r, u to t. That is the only difference. Everything is same. Dou u by dou y by dou t, plus, so this is where through x first we write this. Through x first we write this. Next, second part, through y. Dou u by dou y into dou y by dou t, like this. Now it is a method of writing the derivative formula. Right? Now this is a chain rule for partial differentiation. We go to next page, 11f. Fourth one. Implicit differentiation implicit differentiation. Already we know the implicit function. So for example, the function is like this: y equal to f of x equal to x square plus e power x plus 2, like this. Now for this function of one variable, that is y is written in terms of one variable, means it is explicit function. It is first of all, one variable is written in terms of other variable. It is a explicit function. For this explicit function, we can have the derivative dy by dx directly. 2x plus e power x. Suppose the function is given like this: x square minus x y cube plus 4y plus 2 equal to 0. It is a explicit function. For this explicit function, if you want to find the derivative like this, we can write the derivative directly only. And this function is not explicit function, it is implicit function. And for this implicit function, if you want to write the derivative dy by dx, one method is like this. We take the d by dx on both sides. We take the d by dx on both sides. And then we differentiate every term separately only. We are differentiating with respect to x. First term is function of x only. Its derivative is 2x plus, sorry, minus. In the second term, we have a product of two variables, independent and dependent. Because of this dy by dx, y is the dependent variable, x is independent variable. So use a product rule for second term. X derivative 1 into y cube plus x into y cube derivative is 3y square into dy by dx. plus 4 into dy by dx plus 0 equal to 0. Now we got dy by dx. We simplify this and we try to write the dy by dx in terms of all other only. From these two, we take the dy by dx as common and then we write the dy by dx in terms of all other. In this way, we can write the derivative dy by dx for implicit function. For this explicit function, it is a method of writing the derivative. For this implicit function, it is a method of writing the derivative. But like this, derivative may not be possible for every implicit function. Like this, derivative may not be possible for every implicit function. Or sometimes it may be difficult to find the like this derivative for implicit functions. So in such case, we can write the same derivative in easy way by using the partial derivatives. Such a differentiation is called implicit differentiation. We read that result here. If f of x comma y equal to 0 is an implicit function of two variables x and y. It is an implicit function of two variables x and y. Then dy by dx equal to something by something, that is numerator by denominator. In the numerator, dou f by dou x. In the denominator, dou f by dou y. Or in short form, minus f suffix x divided by f suffix y. That's it. This is a simple method. Using the first order partial derivatives, we can have the first order derivative for this implicit function only. But this implicit differentiation is not only for implicit functions, we can use this for explicit functions only. Whenever the explicit function is like this, sum of many terms like this, sum of many terms, not only this 2, 3, 4, if we have sum of many terms in the explicit function. In such case also, if you want to write the derivative, we can use this only. So this implicit differentiation method is not only for implicit, it is also for explicit only. So we can use this for both explicit and implicit only. It is a method of finding the derivative for implicit functions. Next, Jacobian. Jacobian of two functions. If u of x comma y and v of x comma y are two functions of two independent variables x and y, then the second order determinant along the first row, dou u by dou x, dou u by dou y. Along the second row, dou v by dou x, dou v by dou y is called the Jacobian of u and v with respect to x and y, and it is denoted by dou of u comma v by dou of x comma y, or j of u comma v by x comma y, or just j also. In the next sentence, therefore j equal to dou of uv by dou of x comma y. Equal to second order element u2 xy v2 xy. That is dou u by dou x, dou u by dou y. Dou v by dou x, dou v by dou y. Jacobian of two functions. In the same way, we can have the Jacobian of three functions only. Suppose if we are given three functions of three variables, then we will have third order determinant, that is the Jacobian of three functions with respect to three variables. This is useful to convert the one coordinate system to other coordinate system. Jacobian is one type of transformation which converts one coordinate system to other coordinate system only. Now we write the same thing for three functions of three variables as a note point. Note point number 1. If u equal to u of x, y, z, comma v equal to v of x, y, z, and w equal to w of x, y, z, then j equal to dou of u, v, w divided by dou of x, y, z equal to third order determinant. Along the first row, u2x, u2y, u2z, u with respect to x, u with respect to y, with respect to z. Next, second row for v, third row is for w only. Dou u by dou x, dou u by dou y, dou u by dou z. Next, second row is for v only. Dou v by dou x, dou v by dou y, dou v by dou z. Along the last row, dou w by dou x, dou w by dou y, dou w by dou z. Like this, for any number of functions in terms of any number of variables, we can write. Note point number 2. If j equal to dou of u comma v by dou of x comma y, and j star equal to dou of x comma y by dou of u comma v. Then j into j star equal to 1. That is, if out of these two Jacobins, if you know the any one Jacobin, we can add the other Jacobin by using this result. J into j star equal to 1. Right? Now, let us do the problems on all this. Let's start with the first problem. Problem number 1. If u equal to x cube plus xz square plus y cube plus xyz comma where x equal to e power t comma y equal to cos t, next z equal to t cube, then du by dt at t equal to 0 is option A 3, option B -3, option C 9, option D 4. Now it is a function. U is a function of three variables x, y, z. U with respect to any one of the variable x, y, z is the partial derivative, but we are asked to find the ordinary derivative du by dt only. So this du by dt depends on the other variables only. U is in terms x, y, z. Again, x, y, z are in terms of other variable t only. All three are in terms of single variable t only. That is why u is a function of one variable t. So it is a composite function of one variable t only. That is why this du by dt is possible. And the name of this derivative is total derivative only, because it is a composite function of one variable. First, draw the diagram. From the diagram, write the formula and then find the derivative at a particular point t equals 0. Already you know the method of writing the formula. Just write down the formula and find the derivatives. U is a function of t. So derivative is du by dt. That's why it is a total derivative only. Now from this diagram we write the formula. Now du by dt equal to u to x, x to t. U to x, x to t. U to x, y, z is partial, x to t, y to t, z to t is ordinary only. So dou u by dou x into dx by dt only, plus dou u by dou y into dy by dt, plus dou u by dou z into dz by dt. Right? This is a formula for given function only. From this diagram, we can add the formula like this. All functions are known, find the derivatives and we substitute only, which implies du by dt equal to u with respect to x is 3x square plus z square plus 0 plus yz into dx by dt. X equal to e power t only. With respect to is e power t plus u with respect to y 0 0 3 y cube plus with respect to y is xz, and here y with respect to t is minus sine t plus dou u by dou z with respect to z is 0 plus 2xz plus 0 plus xy into z with respect to t is 3t square. This is the derivative du by dt, but we require the value of this derivative at a particular point t equals 0. On right hand side, total function is not in terms of t only. So some are in terms of t, some are in terms of xyz only. Let us write the xyz also in terms of t value only. Here at t equal to 0, x, y, z equal to x is e power t, y is cos t, z equal to t cube only, equal to. When t equal to 0, this becomes e power 0, 1, cos 0, 1, t equal to 0. Therefore, du by dt at t equal to 0 is also same as the du by dt at 1, 1, 0. That is x equal to 1, y equal to 1, z equal to 0, and also t equal to 0. E power 0, 1, z 0, 0, 3 into 1, 3, 3 plus next sine 0, 0, t equal to 0, 0, 0 plus 0 equal to 3. That is the answer. Right? Like this, we can find the total derivative. Let us go to the problem number 2. Second problem. If x power y plus y power x plus c equal to 0, then dy by dx at 1 comma 1 is option A, E, option B, 0, option C, minus 1, option D, 1. Again, we require the ordinary derivative dy by dx. And we are given some function in terms of two variables. We are given some function in terms of two variables. To find the dy by dx, first we check y is in terms of x or x in terms of y or not. If you are able to write the y in terms of x from this, directly we write the dy by x only. Or if you are able to write the dx by dy also, we can write this only. But here, we cannot write the y in terms of x. We cannot write the x in terms of y. Therefore, it is an implicit function. Because the implicit function, in easy way to find this ordinary derivative, we use the implicit differentiation only. We use the implicit differentiation. So to use implicit differentiation, let us consider this as implicit function only. Let f of x comma y equal to x power y plus y power x plus c. We are taking this as an implicit function in terms of x and y. According to this implicit derivative, this is given by minus fx by f5 only. So we try to find the first order partial derivatives of this. Then fx, that is dou f by dou x. And we find the fy, that is dou f by dou y. Now, in every term, the something in place of base we have something, in place of power also we have something only. So x power y, y power x. Base is x, here power is y. Here base is y, power is x only. So something for something means we may require these two formulae only. D by dx of x power n equal to n into x power n minus 1. Similarly, d by dx of a power x equal to a power x into log a only. We can use these two formulae because something power something only. These two formula both are functions of x only and both are with respect to x. Then the difference is in first one, base is variable, power is constant. Here, base is constant, power is variable. So using these two, we write the derivatives of this. Now, first, we are finding the partial derivative of f with respect to x. When you are doing with respect to x means x is variable, independent variable. That is, it is a partial derivative only. When you differentiate partially with respect to one variable means other variable must be constant. So here we are doing with respect to x means other variable y must be constant only. So in the very first term x power y, base is variable, power is constant. Base is variable, power is constant. That is x is variable, power y is constant. For this, we use the first formula like this only. That is y into x power y minus 1 plus. Next, for second term, we are differentiating with respect to x only. So y must be constant only. So base is constant, power is variable. Y power x is in the form of a power x. So use this formula only. Y power x into log y. That's it. This is the fx only. Similarly, we can find the fy only. Differentiate f partially with respect to y. When you are differentiating f with respect to y partially, we treat other variable x as constant only. In the very first term, base is variable, power is constant only. Base, sorry, we are doing with respect to y. In the very first term, base is constant, power is variable. Base is constant, power is variable. Then use the second formula. That is x power y into log x plus. We are doing with respect to y. In the second term, base is variable, power is constant. For this y power x, we can use the x power n formula. X into y power x minus 1. Now we know the two derivatives, we can add the ordinary derivative. Now dy by dx equal to minus fx by fy, which implies dy by dx equal to minus fx is y into x power y minus 1 plus y power x into log y divided by x power y into log x plus x into y power x minus 1. Therefore, dy by dx at 1 comma 1. That is x equal to 1, y equal to 1. Log 1, 0, log 1, 0, 1 into minus minus. Here log 1, 0, 1. So finally it is minus 1. It is the answer. This is about implicit differentiation. For composite functions also, sometimes we may require this implicit function differentiation. Now, let us do the problem number 3. If u equal to x into log of xy, comma, where x cube plus y cube plus 3xy equal to 1, then du by dx is du by dx is. U is a function of two variables. So the derivative of u with respect to any one variable is partial. But here we are asked to find the ordinary derivative. So this depends on the other variable relation. Now first we draw the diagram from the given relation. U is given in terms of two variables, x and y. Again, x is not given in terms of any other variable, y is not given in terms of any other variable directly. That is, here from this relation we cannot write x in terms of y, we cannot write y in terms of x. This is an implicit relation only. So this is unknown, this is unknown, this is unknown. With these two unknowns, we cannot write the u in terms of other variable only. So this is also unknown. That is u of something unknown only. But here we are asked to find the du by dx only. If we can fill these three gaps, 1, 2, 3, then we get the formula only from the diagram. Okay, it's like this, page number like this. This is unknown. This is unknown, but we require this only, like that here. Now, based on this required derivative du by dx, we can add these three unknowns only. Just look at this one. Du by dt. And this is ordinary derivative. Ordinary derivative is only for function of one variable only. In this derivative, u is a dependent variable, t is an independent variable only. And here this u is coming from first term or first variable, and this independent variable t is coming from this last variable only. That is why this is the du by dt. Because of this du by dt, this is the derivative for only function u of t variable only. From this we can add the u as a function of t. That is this here only. Again, when u is a function of t, we can add the u as starting variable, t as last variable, like this. Okay. Let us look at this du by dx only. We require the du by dx. It is ordinary derivative. And because of this ordinary derivative, u is a dependent variable, x is independent variable. This is a derivative only for u of x only. It is a derivative for u of x function. From this, we can say that u is first variable, this x is last variable only. If it is a function of one variable, these two must be x only. That's it. Diagram is completed. That's it. Just like this only. Just like this only. Now from this diagram, we can add the formula. Now du by dx equal to u to x, x to x, u to y, y to x. Dou u by dou x, again dx by dx only. Plus dou u by dou y into dy by dx, which implies du by dx equal to u with respect to x is u is x into log of xy. Log is a function of x and y. It is also just a function of x. Because of both contain the variable x, we use a UV rule. X into derivative of log is 1 by xy. Again, xy with respect to x is y. Plus log into x derivative is 1. So log of xy into dx by dx, or d by dx of x. Derivative of x with respect to x is 1. Plus u with respect to y. This function x is free from y. So just you have to differentiate only log. X into log derivative is 1 by xy. Again, xy derivative with respect to y is x. Into dy by dx. We can find this dy by dx from this relation only. From this relation, we can find this dy by dx only. But from this relation, we cannot write the y in terms of x to write the dy by dx directly only. So in this case, we use the implicit differentiation method only. We use the implicit differentiation because it is implicit function only. This implicit function is given by here minus fx by fy, comma, where f of x comma y equal to x cube plus y cube plus 3xy minus 1. Right? It is a function, implicit function. Directly by differentiation, term by term, we can write the dy by x, or we can use this implicit. But using the implicit differentiation method is simple only. Here we should find the dy by dx. We can find the dy by dx only from this relation x and y. But here we cannot write y in terms of x. That is why we are finding the dy by dx using this implicit differentiation only, which implies du by dx equal to x get cancel, y get cancel. So it is 1 plus log of xy plus x get cancel, x by y into minus of fx is. From this f of x, the partial derivative of x with respect to x is 3x square plus 3y divided by the partial derivative of this with respect to y is 3y square plus 3x. And 3 is common. Therefore, du by dx equal to 1 plus log of xy minus 3 get cancelled, minus into 3x cube, sorry, just x into x square, 3 x cube plus no 3, only xy divided by y cube plus xy. Now this is the result. Here we cannot find this dy by dx directly. That is why we are finding this dy by dx from this implicit function by using implicit differentiation method. Just now I told you that while finding the total derivative, we may require the like this partial differentiation implicit method. Okay, let us go to the problem number 4. If u equal to x plus y square by x and v equal to y square by x, then dou of u comma v by dou of x comma y. Option A, x by 2y. Option B, 2y by x. Option C, minus x by 2y. Option D, minus 2y by x. So dou of u comma v by dou of x comma y is the Jacobian of transformation. It is Jacobian of u and v with respect to x and y. Now j equal to dou of u comma v by dou of x comma y equal to second order determinant dou u by dou x, dou u by dou y. Here dou v by dou x, dou v by dou y, which implies j equal to u with respect to x is 1 by x derivative is minus 1 by x square, and u with respect to y is 2y by x, and v with respect to x is minus y square by x square. V with respect to y is, sorry, u with respect to x is 1 minus y square by x square. U with respect to y is 2 with respect to y is 2y by x. Next, v with respect to y. V with respect to y is 2y by x. Which implies j equal to product of diagonals minus product of non-diagonal elements. 2y by x minus 2y cube by x cube minus minus plus 2y cube divided by x cube. This to get cancelled. Therefore, j equal to just 2y by x. Next, problem number 5. If u equal to 3x minus 3x plus 2y minus z, comma v equal to x minus y plus z, comma w equal to x plus 2y minus z, then dou of u dou of x y z divided by dou of u v w. Option A -2, option B 1/2, option C -1/2, option D 1. It is similar to previous one, but in the previous one, that is Jacobian of only 2 functions. Here, Jacobian of 3 functions. We are given that u in terms of x, y, z, and v in terms of x, y, z. W is in terms of x, y, z. Whenever u, v, w are given in terms of x, y, z, directly we can find a dou of u, v, w with respect to x, y, z. It is a Jacobian only. If u, v, w are given in terms of x, y, z, we can find this Jacobian only. But here, we are given that u in terms of x, y, z, but we are asked to find the Jacobian of x, y, z with respect to u, v, w only, reverse. For given u, v, w in terms of x, y, z, directly we can write this Jacobian only. But we are asked to find the reverse. We are asked to find the Jacobian of x, y, z with respect to u, v, w only. From the given 3 functions, if we are able to write x, y, z in terms of u, v, w, directly we can write this. Not possible to write, then we can use the note point number 2 after Jacobian only. This note point. Page number 13F, note point number 2 only. If you know the any one Jacobian, we can add the other Jacobian. It is advantage. So first we find the Jacobian of x, y, z with respect to u, v, w. But we find this indirectly with the help of this Jacobian only. Okay. Let us find this one first for given functions. Now, we have to find only this, but first we have to find this only. Using this only, we can add this value. Let us suppose j equal to dou of u, v, w divided by dou of x, y, z. This is equal to third order determinant. Along the first row, dou u by dou x, dou u by dou y, dou u by dou z. Along the second row, dou v by dou x, dou v by dou y, dou v by dou z. Along the last row, dou w by dou x, dou w by dou y, dou w by dou z. This is equal to which implies j equal to u with respect to x, 3 with respect to y, 2 with respect to z is -1. Next v with respect to x, 1 with respect to y, -1 with respect to z, 1. Next w with respect to x, 1, w with respect to y, 2, w with respect to z is -1. And if we expand this determinant, we get the determinant value. Now, what is the value of this third order determinant? If anyone tells, I'll write directly on. What is the value of the determinant? -2. Okay. Now, some are saying that -2. Okay, I'm writing the -2 without calculating because one of you got -2. Since j into j star, j into j star equal to 1, which implies j star equal to 1 by j. Here j is -2 only. Therefore, j star equal to dou of x, y, z divided by dou of u, v, w equal to -1 by 2. If j is -2, then j star will be -1 by 2. Like this we can find. So this is about Jacobian only. So with these problems on the partial and total derivative topics are completed. The problems on this topic are completed on. So with this, I close the session. If you have any doubts, tomorrow I will clarify. Today we don't have a doubt session class. Tomorrow I clarify your doubts. Try to write all the doubts on paper. Tomorrow you can ask me.